Hello and welcome. This is Lab 7, the benzopinacalone rearrangement, and let me explain a little bit about it before I take you through the procedure and get the results. This is pinacole, and under refluxing acetic acid conditions with a crystal or two of iodine, water is lost and you form pinacalone, so it's a rearrangement, okay? Water is lost and you form a ketone from a vicinal diol. Vicinal means adjacent, so basically you have one OH on one carbon, and next to that, right next to that, you have another OH or hydroxyl group on the carbon. So we call that a vicinal diol. And this is a rearrangement. It's traditionally called the pinacole rearrangement, okay? It was discovered by Wilhelm Rudolf Wittig in 1860. One of the post-lab questions is asking you what country was Dr. Wittig from. The correct answer is not Germany. Germany was founded in October 3rd, 1990. Germany was called many different things, the Roman Empire and other kind of things, before it became Germany in 1990. So check to see what it was called in 1860. It's a little bit of a cultural, historical activity for you. Now in the lab, we're going to be taking benzopinacole that we synthesized from benzophenone. Remember, we put benzophenone in isopropanol in the sunlight. We did a photochemical dimerization reaction basically to form this product, okay? So we're going to take 5 grams of that in 25 milliliters of acetic acid with 3 crystals of iodine and form benzopinacole, okay? Water is going to be lost during the reaction mixture. Now, sometimes we don't have exactly 5 grams. Maybe our reaction only gave exactly 2.5 grams. Now, 2.5 grams would be half of that. So to figure out how much acetic acid we use and maybe how many crystals of iodine we use, we have to do a scaling, all right? Just like you do in cooking, okay? If you have the recipe, you have all of the components. So if we only had exactly 2.5 grams, there would be 0.5 times as much acetic acid, which would be 12.5. And half of 3, well, that's like 2 or something, okay? 1 or 2, you decide, okay? Like when you get the hamburger at McDonald's, you might have 1 pickle, you might have 2 pickles. They're not gonna put 1.5 pickles on a hamburger, okay? So yeah, if you have 3 grams, just do the math to figure out how many milliliters of acetic acid you'll do. Show your calculation for that. I'm just gonna go ahead and pop it in the video so you'll see what your answer should be, but I'm just gonna go ahead and weigh it out, do the math quick on my calculator, and then use the correct amount of acetic acid for the chemical reaction, okay? Now, one of your activities is to draw the curved arrow reaction mechanism for this reaction we're doing in the lab, the bottom one, okay? Benzopinacole to benzopinacalone. I'm going to show you the curved arrow reaction mechanism for pinacole going to pinacalone. Basically, it's the same exact thing, except instead of methyl groups, you have phenyl groups, okay? By the way, I should mention, I'm not going to involve iodine in the curved arrow reaction mechanism. Down in question 5 of this lab question, I ask you, what is the purpose of iodine in this experiment? And I say in parentheses, right, it's a catalyst. But which step or steps in the mechanism does it act? Show the mechanism, okay? And I say it's optional, extra credit. I'll boost your grade by 20%, whatever you get on the lab. Don't message me or ask me in person, hey, is it because blah, 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 blah. I don't know what the answer is, okay? I haven't had time to go search the literature and read up about this and how iodine can act as a catalyst, okay? I don't know how it works. Anyways, I'm just gonna show you the uncatalyzed reaction, which is acetic acid directly reacting with that, okay? So let me show you the curved arrow reaction mechanism. For acetic acid, I know it's a weak acid, but I'm basically going to treat that as H+ to simplify the amount of stuff we have to write on the board, okay? So the first step we have is as I've taught you, if you have acid, use that in the first step. So let's protonate. Protonate that alcohol, okay? So we're going to protonate that guy here. As I've been teaching you, water is a good leaving group, so we can make that depart at this stage of the game. That probably is the slow step. Why would that be the slow step? Why would going from here to the next thing I draw have the highest activation energy? Well, because I'm going to be drawing a carbocation, okay? Fast steps are generally in equilibrium. Slow steps, we usually use a one-way arrow, okay? So once you form the carbocation, that's going to be it's going to be downhill from there, okay? So this is the hardest step, the rate limiting step or the rate determining step. So this is a tertiary carbocation, pretty stable, you know, I mean, relatively speaking, but we can make it even more stable. If we scoot a methyl group from this carbon over to that carbon, we do what's called a 1-2 rearrangement. And if we do a 1-2 rearrangement, we can form another carbocation, but let me show you what's so special about this one. This carbocation really isn't even a carbocation. The reason why is because the resonance structure is so much better because every atom in the molecule has an octet. Remember, if everything has an octet, that's going to make a molecule unusually stable, especially in comparison to a carbocation where this carbon only has 3 bonds or 6 electrons in total. So there you have the carbon-oxygen pi bond. Your ketone is protonated on the oxygen. And so now we just need to deprotonate that with acetate, acetic acid, or water that's in the reaction mixture that's formed in this step. So here's where you lose water, okay? So I'll use acetate here to deprotonate this. Acetate in this step reforms acetic acid, which was used in the first step. So it's a catalyst. The acid does a protonation, all this happens, and then there's a deprotonation, and you make the acid back again. I always wondered why they called this pinacalone. There is actually a bottle of pinacalone back in our chemical supply cabinet, and I smelled it, and it has just a very rich pine kind of cologne odor to it. So this is a very nice smelling compound, interestingly enough. So that's the lab, that's the detail behind it. Now let me go ahead and do the experiment so you can see things boiling and filtering and transferring, okay?